Good evening, everyone. Welcome to our week 5 review session for business analytics. How has it been going for the past week?
Hi, it's been doing good.
Glad to know that.
Thank you.
Any questions regarding homework 5? This time we are solving 2 time series regression models.
Hi, Jerry. I did have, this is Lala. Oh, sorry.
Hi, Lala.
Hi. Yeah, okay. I did have a question on 1E.
Okay. What are your questions regarding 1E?
So this one explained, let's see. No, actually, I think, yeah, it was, yeah, E. So this one explained why exponential smoothing doesn't, that's what I had. I had the exponential smoothing. Can't make a prediction past week 18 because it doesn't know what week 17 is.
Yeah, sounds right. But you expect it should work further?
Well, no.
Oh, okay.
Okay, by definition, right? It doesn't. It can't predict further into the future. I wasn't sure if that was the reason. That's my understanding. Is that correct?
Oh, that depends on which part you're addressing. So one question is regarding which of the 2 models we can use to predict for week 18, right? That's 2 weeks ahead. Then in that case, we could only depend on the regression model with the square of time in it, because exponential smoothing, as you found out already, could only go 1 step ahead.
Okay, yes, the second order polynomial, right? That one can actually predict ahead because it's an actual model.
Yeah, I mean, both are models, except that exponential smoothing is confined so that it predicts for 1 step ahead.
Just 1 step ahead. Okay.
Yeah, as the formula shows, it needs the previous step to predict the next step, right? So if we have not observed week 17, then we won't be able to predict week 18.
Okay, yeah, that makes sense to me. And then one more on letter 1C, where, which one is more appropriate? That one.
How did you address that part?
I struggled either way because it looked like another model would fit better. But at the same time, the nature of the data fits exponential smoothing, in that the difference for each data point from the mean seems to be random. But
excuse me, I was slightly lost. How did you address? How did you make your selection?
I said that it does resemble exponential smoothing, but I was not confident in that answer.
Lala, would you mind if I try to expand on that a little?
Sure.
Jerry, I kind of struggled with this too, but what I wrote, and I think I'm hoping it's correct, but you'll be able to let us know. Oh, sorry, your screen sharing threw me off. I put that because there's some random fluctuations around the horizontal line, it indicates that it's a stationary time series, which smoothing techniques are an appropriate way to model the data set. I just didn't know if it was that simple of an answer.
The answer is simple, however, the reason is totally the opposite. What I heard from you is that you claim that this black dot, that's the original data, right? I'm sharing my screen of the Excel file I have. So this is the scatter plot. I heard from you that you said it's stationary because there's random fluctuation. However, it's not stationary. What is the stationary time series is that the mean value should be on the horizontal line, so it doesn't change over time. However, we do see there's a trend upward over time. That makes it non-stationary.
Yeah, my chart looks nothing like that one. So, okay.
Oh,
Okay,
really?
so
Okay.
this goes to my question, because I looked at the data, I did an initial scatter plot, and then I chose the exponential model, but we have not talked at all about exponential. It curves up, so.
What did you mean when you say you were not taught about exponential? I believe
Oh, I'm sorry.
Lecture has already, discussed what exponential smoothing is.
Apologies. Okay, so no, it was another one. Let me pull up that sheet and go.
Oh, okay. Are you? Was your question about problem 2 then? We have 2 problems this time. One is about attendance. Number of visitors to a new shopping mall. And the next is about the number of customers to a bank. So I heard that someone commented that they had a very different scatter plot than what I do here. If it happens, maybe what happened is that the selection of the horizontal axis and the vertical axis were wrong. So make sure you check the range of what the horizontal and vertical axis show.
Jerry, it's Tiffany. It's T. But I'm looking at so for the chart that you have, the scatter plot that you have there, just looking at your R squared, I have the same thing when I did the second order polynomial regression. So that chart does look the same, but the chart that looks different for me is when I answered question 1C, which is, I believe, what Lala's asking about.
Okay.
That's not when we did the second order polynomial. So I have a totally different R squared. Does that make sense? The R squared you have on there, I have later on for D.
Okay. So did you mean that you got a second R squared?
So for C, I have a different R squared. And then for D,
Okay.
when we do the second order polynomial where we add a quadratic column, a variable column, I have the same R squared that you have on that graph.
Yeah, because they are about 2 different models, right? If you were talking about R squared in C, it's not required, because in C, we are simply assessing whether exponential smoothing model is appropriate. And it doesn't need, it's not necessarily quantitative, because we could address this question solely based on what exponential smoothing model is appropriate for. As we discussed just now, it's for stationary models. That's where the mean of the time series does not change over time. So that's what makes exponential smoothing not appropriate for this type of model where there's a clear trend over time.
Okay, got it. Thank you.
Yeah.
Okay.
However,
Yeah.
did I address your questions already?
Yes.
Any further explanations?
Yeah.
I think for Lala, but I think for me, I'm just confused. Maybe I'm misreading the handout from the professor, but I recall reading that if there's some random fluctuations around a horizontal line, it indicates that it's a stationary time series, and he says that smoothing techniques are appropriate to model that type of data set.
Yeah, but did you notice that there's a fluctuation around the horizontal line?
Okay, so it should
but
be
here,
flatter.
the dots are not, around a horizontal line. It is instead a, let's see, parabola, right? A parabolic line. So that's what makes the time series not stationary. So we call this type of series non-stationary series.
Got it.
Because there's a
smoothing
trend
techniques-
in mean.
So in this event, for this, the second order polynomial would be more appropriate.
Yes, correct. As you can
Okay.
see here, I added two theories of trend line. Well, not really trend line, it's just dots. So as you can see, the black dots I have here are the original data points. It represents the week index and the number of shoppers. That's what black dots mean. So if we build the model in part D, that's the second order polynomial regression model. It's nothing but a linear regression with both x and x squared, right? So x here is the weak index. That's what forms this orange or yellow color line. And as you can see, because all the dots are predicted values, so they line perfectly on this parabolic line, because this line is the predicted value or the predicted line. In contrast, if we depend on the exponential smoothing, this is what the green line represents, as well as the green dots. Because the smoothing technique is based on this formula. It's a weighted sum of what happens beforehand and what the previous prediction was. So it's not a parabolic trend line at all. However, because this time series does increase over time, right? So it has an increasing trend as well. But because the recent increase is not fully weighted, it was smooth using, let's see, what's D2? Yes, this most recent observation is smoothed by this parameter 0.4. So only 40% of the increase in the most recent observation is captured in the prediction. So that's why it's increasing slower than the observed time series. That's why you see the green line is lying beneath the yellow one. And if we made a prediction for week 18, by simply dragging this automatic autofill, what you notice is that it does make a number for week 18. However, do notice how this is formed. The week 18 prediction, if we based on exponential smoothing, is still calculated as the weighted sum between this cell, which is empty, and the last prediction. So an empty cell in Excel is sometimes recognized as 0. Sometimes it will show as an error. And this time, because it's just the sum, it's recognized as 0. That's why you see it's very low. So do notice that Excel often allows you to use a formula to generate some outcome, but this prediction is totally a mistake because it treated an empty cell as 0. And reflected on the plot is that the prediction for week 18 is totally off the trend. All right.
I'm sorry, Jerry. So just to understand, so because those are empty, when they're doing the prediction, it's saying that it's 0, so those predictions are not correct or accurate, correct? Like the
Correct.
17 and 18, and that's why you see that almost like that dip, right?
Mhm.
Okay.
Yeah, it also highlights that exponential smoothing is only appropriate to go one step ahead. Notice is that this point, that's week 17, that's 1 week ahead of what we observed in week 16, right? It's somewhat okay, but going another step forward, then it's not, because we could not have we did not have an observed value for week 18, for week 17. All right, any questions regarding problem 1? We have just demonstrated how to do exponential and second order polynomial regression model. All right, how about we move on to problem 2? In this problem, we have to create a few dummy variables to indicate the shift. There are 5 shifts. However, we also have 2 weeks of observation. Any questions in problem 2?
Yes, I'm not sure how to do that.
Oh, okay. Have you done any part in problem 2?
So what I did was create the dummy variables, but then I kept running the regression and getting errors because I was including non-numeric columns. So
Oh,
what
okay.
I'm not clear on is what is being modeled here. Is it just the dummy variables to predict the number of customers that come in the bank?
No. It seems first you selected a wrong column where it contains text instead of numeric values. And second is that here, as the model clearly says, we are developing a multiple regression model. So first is regression model, and that means there needs to be one and only one dependent variable, and there could be one or more independent variables. So here, the independent variable, as clearly announced here, it's a trend and a seasonal component. However, even without knowing that, depending on how this data is generated, we could also have some understanding about what the data shows. This time series is the observed number of customers who visited a bank, right? So this is the dependent variable number of customers. And I believe the original data sheet is only these 4 columns. All the rest columns were what I generated afterwards. So what happened is that to indicate the shift, instead of this text entry, which Excel cannot understand at all, we have to transform the shift by indicating it using a few dummy variables, like what I did here, using shift 1, 2, 3, 4 in one of the models that I have. For example, this one is a candidate output. However, it's possible that you specify your model in different ways. For example, instead of shift 1 to 4, you could use shift 1 as the reference, and used shift 2 to 5 as the predictors or the independent variable in the regression model. Recall what we practiced in the last week homework and review session, and also the week before the last, where we built dummy variables as indicators. Any questions regarding how the indicators were built?
Jerry,
Hi.
this is T.
Hi.
I think I did that correctly, but my question is for the actual like equation itself. Could I
Okay.
show you what I have and you just tell me if I'm on the right track?
Yeah, sure. How about you share your screen with me?
Sure. So this is how I did the variables for each one. So essentially taking the intercept plus,
Okay.
can you see my screen?
Yes, I can.
Okay.
Okay.
Yeah, the intercept, and then, whichever respective shift, or this is a shift 1 plus the period
Okay.
times whatever assigned period we gave to that shift in this column. And then I just did that for 2, 3, 4, and then for 5, there's no intercept, right? Because we know that it's 0.
Mhm.
So I just want to
Yeah,
make
looks
sure.
right to me. Yeah, this is a great way to show the result. However, do notice that there's only one intercept, but those coefficients for shift 1 to 4 are could be combined with the intercept just for us to understand what it means. However, usually those are not directly referred to as intercept.
Are you saying this? We could just do the math there instead of having it
No,
this
I'm
way?
saying that the coefficient that's negative 2.02 for shift 1 is usually not referred to as intercept.
Hmm.
But you did correctly. So we could combine the coefficient with intercept because it means what happens for shift 1 when
Mhm.
period is 0.
Okay, got it. Okay. Thanks, Jerry.
Yeah.
Just so I'm clear on that. Okay, can you share again? Because you were saying it's 39.6 is the intercept, but then you would say plus and then the slope, right? And times 0 or 1.
Yeah, that was another student's question, right? Were you which part did you not find clear?
My question is on shift 1 where it says customers equal the 39.6. So that in the equation, the regression equation,
Mm-hmm.
you're saying this is not the intercept. This 39.6 is the intercept, but not the negative 2.02.
Yeah, as a list on the coefficient table, because as you can see on the left column of the regression table, the intercept is 39.6, whereas the coefficient for shift 1 is a negative 2.02.
Okay, thank you.
Yeah.
Jerry, if we could just kind of piggyback off of that, since we're asking about it, that's okay. In question, where is it? Sorry, in question 2A, where it's asking us, how would we interpret all the slopes / coefficients?
Yep.
Um,
That's very important.
It is, yeah. I'm not really sure what I'm being asked there.
Okay. You're not sure what it asks for? Let's see. Carefully describe how you build the model and how you would interpret all the slopes and the coefficients except for the intercept. We practiced the same procedure previously. First, we simply describe how the independent variables were created. This is exactly the procedure I demonstrated a few times before. Simply announce how, for example, on this, you could say that I created 4 or 5 indicators but only used 4 indicators in a model because the shift has 5 unique values, right? From 10 to, let's see, from 8 a.m. to 6 p.m. So 5 different categories. That's why we need 5 minus 1, that's 4 different dummy variables to represent a categorical variable that has 5 categories. Then describe how each variable, dummy variable, is built. For example, I created an indicator for shift 5 so that this variable takes value of 1 when an observation was made on the last shift on each day, or 0 otherwise. So that the job is done in terms of how the model was built. Simply, it's about how each of the variable was defined. Maybe we also had to generate the period value, right? So there could be multiple ways to generate period. We can evaluate each of them very soon. So one typical way, what the professor did, was using the simple one, starting from 1 as the first observation to 50 as the last observation. Yeah. However, you could possibly use some other sequences to represent period. So we simply need to announce, oh, in the model, we have period and 4 shift indicators as 5 different independent variables, whereas the number of customers becomes the dependent variable. That's what makes the model building description complete. So when we interpret slopes and coefficient, we simply need to refer to this regression table and interpret what each of these values means. So how about we try them? Would anyone like to try what this intercept represents? Feel free to unmute yourself and try and join us in the practice how we could interpret an intercept in a regression model. Anyone? Okay. How about Rachana? Would you like to try how you would want to interpret an intercept in a regression model?
Yeah, I think it's where on the y-axis your line meets the y-axis, that difference, right?
I'm sorry, I'm not sure whether I understood that part. Understood what you described. Could you elaborate?
So you have the dependent variable on the y-axis and the independent variable on the x-axis. So
Okay.
if you extend your model to meet the y-axis, it should be like 39.6 units above.
Oh, I see. Okay. Conceptually, it could be right. However, do notice that here we have what's called as a multiple linear regression. It means we have many independent variables. So if we draw a graph, a scatter plot, there are many dimensions we could show. So sometimes it's possible to draw a 2-dimension graph. So we have one horizontal axis and one vertical axis. However, in many cases, it's we could only confine the horizontal variable to be one of these few. So interpreting the intercept using a graph or a scatter plot is sometimes limited when there are too many variables, so that there could be many different scatter plots we could draw. So in this case, a good and a simple way to interpret intercept is that when we hold all the predictors to be 0, the predicted value of the dependent variable, in this case, the number of customers to a bank, is 39.6.
Okay. Yeah, thank you.
Well, good try. However, as we also demonstrated a few times in our previously week review sessions, the intercept may not always have a tangible meaning in it. So, for example, let's consider whether it's reasonable to hold all the variables to take a value of 0. What do you think?
No, because these are the bank office hours, right? I mean, there has to be some time they're in the bank.
Oh, sorry, excuse me. What did you indicate?
I said that shift hours,
Okay.
each of these represent the hours that the bank is open. So if none of the bank hours are open, then the intercept, right, would say that there's almost 40 people in a bank, but the bank isn't open.
Oh, I see. You are both right and wrong. You're right in that in this case, the intercept may not have a tangible meaning because it's not possible to have all the predictors to take value 0. However, when the predictors take value 0, it doesn't mean the bank is not open. So notice how we defined each of these 5 variables. First is a period. The period is nothing but a sequence of time. We could, here in this model we just saw, it's defined as 1 to 50. So if this period is taken a value of 0, let's think about what it means. 0 is not observed in the 50 observations. However, it's before what period 1 stands for, right? So it would represent if period 1 takes value, the variable of period 1 takes value 0. It would mean the previous week's last shift. So it'd be Friday in week 0 and shift 4 to 6 p.m. But let's also go to the other indicators. In my model here, I have shift 1 to 4, so that shift 5 becomes the reference level. So if shift 1 to 4 all take value 0, what does it indicate? As you can see here, the very way we define these indicators makes it so that if shift 1 and 4 variable, the dummy indicators, all take value 0, it would indicate shift 5. For example, shift 5 in the last shift on Monday, we have a shift 1 to 4 taking value 0. The last shift on Tuesday also have a shift 1 to 4 taking value 0. It's because I defined these variables in this particular way. So if all these variables, the predictors, we have 5 here, right, take value 0, it would refer to week 0, Friday, and shift 5. That's the last shift on Friday. So you could say that we didn't observe it, but we still have, we could predict that part. But you could also announce that because we did not observe what happened in the previous week, so it was not a tangible meaning in that. Any questions on that part? All right. Now let's see how we could interpret what shift coefficient represents. How about another student? How would you interpret a shift coefficient? Let's start from shift 1. Good. Anyone want to try? How about well, how about loop? Would you want to try how you would interpret what shift 1 coefficient?
You mean Lupe?
Yes, it's Lupe.
Lupe, okay.
It's okay.
Thank you for correcting. Yeah.
No worries. I can try. So for shift number 1, it's negative 2.03.
Mhm.
Honestly, I'm not 100% sure.
Okay.
Yes, I mean, is it that you have
How about
two
Lala?
people?
How
that
would you
have
address that?
Yeah, maybe 2 fewer people in the bank during that shift or time frame.
Yeah, exactly. That's a
people
very
less-
good try.
2 people less visit the bank in that shift.
Yep. So you're partially correct. Partially means that you did make a good attempt to combine a quantitative statement in the interpretation that what this -2 represents. However, we also want to put it in context. When we say increase or fewer or less, we need a reference. In this case, the very reference we had lies in which of the of the 5 shifts we held as the reference category. Because I built the variables so that the shift 5, the last shift on each day, is it's not used as one of these 4 variables in the regression, right? So that makes it a reference category. So every of these 4 shifts are going to be compared with shift 5. And another caveat is that when doing regression or multiple linear regression, when we have multiple variables, we do want to announce particularly that a coefficient is assessing the effect when holding everything else constant. So when we talk about shift 1 coefficient, we want to hold other variables constant. That includes period 1 and other shift indicators. So let's see whether it makes sense. Could we possibly change what the value shift 1 is without changing other value, without changing the values of other independent variables? That includes period 1 and all the other shifts.
No.
Okay, what was your rationale?
So you asked if we could change one without with it not changing or influencing the other ones, correct?
Yeah, but notice that here, what's changing is the value of the independent variable or the predictor. It's not the coefficient, right? Because the coefficient they already estimated. We're talking about whether it's possible to change the value of the dummy variable shift 1 without changing other predictor values.
I would say no, because to some degree, aren't they correlated?
Yes. However, it's we are talking about whether it's possible. It's not whether it usually happens.
Can I try? So
Yeah, sure.
I'm gonna say yes, it's possible.
Mhm.
Because if you change any of the independent variables, then it's going to change your model, right? I think that's what you mean, but again, correct me.
Okay, good try. Although I'm not sure whether I followed your rationale clearly. If I were to answer this question, I would say there's a not so satisfactory in terms of how I generated the period variable. So let's go into them. If shift 1 is changing between 0 and 1, it means whether this observation is made for a one day's shift 1 or not. If it's about shift 1, then it takes value 1, otherwise it takes value 0. This 0 could because the observation was made on shift 2 or shift 3 or 4 or 5. So if we hold each of shift 2, 3, 4 indicators constant, for example, when they are all 0, let's see whether we could possibly change shift 1 value from 0 to 1. We found that it's possible because we observed that both shift 5 and shift 1 would have the variable shift 2 to 4 taking value 0. So between these two shifts, shift 1 and 5, we could actually have shift 1 dummy variable changing between value 0 and 1. However, whether it's true for period 1, could we possibly change shift 1 dummy variable value without changing period 1 value? Let's also go back to how the data sheet. It appears not possible. So for example, if we just focus on shift 1 and 5 on the first day, we do have that shift 2 and through shift 4, all these three variables taking value 0. So they are not changing. They were held constant. And at the same time, shift 1 are changing between value 0 and 1. However, we notice that shift period 1, the integer sequence, is changing from 1 to 5 because this is how it was generated. Then it doesn't seem that it was a reasonable way to announce that, oh, we could switch between shift 1 or not shift 1 without changing the period. So that's why I provided a second way of defining period 2. I noticed that in the chat room, one student asked what period 2 represents. This period 2 is nothing but an integer index of the day sequence. You notice that it starts from 0 for all the 5 Monday observations and increase to 1 for all the Tuesday observations. Then it becomes 2, 3, 4, and to day 10. That's what's observed, because after and to 9, because I started from 0. All these week 3 values were predicted. So with this type of definition of period, that's what our question described as a trend, right? That's an increasing trend in the number of day elapsed. It's slightly different than how period 1 was defined. Period 1 was the number of shifts elapsed since the beginning. Here I use number of day elapsed because there are 5 days in 5 shifts in one day, right? So that's why you see that it's increasing somewhat slower. But does it affect our predicting power? We can find out. Well, how about I regenerate the regression model so we can see the consequence clearly. But before then, it appears that I would have to do something. Let's first, okay, do these. I think I just need to insert these columns because Excel only allows you so that the predictor variables are adjacent. It cannot allow a discontinued region to be selected. I think there's nothing wrong here. So let's run a regression model. You could also review how to do regression again. But at this point, you should be quite familiar with how Excel treats regression models. So first, we select dependent variable. Notice that dependent variable is nothing but the number of customers. And if you made any predictions beyond week 2, notice that our observation only ends on week 2, so we do not go further. And I also select the top row as the variable name. That's why I would claim there's a label of the variable. When selecting, let me make sure I'm selecting X. Yes. So do notice that you want to make sure you put independent variables to X and the dependent variable to Y. But here, well, I don't, okay. This is where the independent variable ends for the first 2 weeks. So I'm going to put the new regression output here. So, oh my God, okay. It appears that I did not select one of the independent variables. So let me redo it. So it's not P, but O. So that I have both period and shifts included. Then it's the same. Okay, now this regression is finished. So let's compare these two different models. How they are different. The period is defined differently. In the first case, we have period representing the number of shifts elapsed since the beginning. On the second, we have the number of days, so they are the value of them are different. Also, we used a different reference category for shift. On the left, the model used shift 5 as the reference category. That's why it's coefficient. It's not estimated because it's 0. Okay, interesting why this shift 5 also has 0. Let me make sure. Oh, I see. It's because the variable was defined wrong. I need to go back so it becomes C. Okay. All right. I would have to redo the regression, but everything was correct except that. Okay, now this time it works. So let's compare these two models. If we go to multiple R, we notice that they are exactly the same. So as R squared, because R squared is simply the square of multiple R. The adjusted R squared is also the same, so as standard error and number of observations. You will also notice that these ANOVA table is also the same. However, the coefficient table is slightly different. Continuing with where we left, the right model has a shift 1 as the reference category, so whose coefficient would be 0. Then we notice that the intercept is slightly different. So as and also the coefficient of period are different. But the shift 1 to 4 have also different coefficient. although their predicting power represented by R squared is exactly the same. Now, would one of you describe why this happens? It appears that we have different predictors and also different coefficients, but the model quality was the same.
The reason would be that the shifts, how they interacting with the period too. So even though the ability to predict is the same, because of that, the change of the period definition has an effect.
Yes. So you are, I think, mostly correct. I'm not sure whether I captured all your thinking here. You did notice that the predicting power is the same. However, I'm not sure whether you understood the reason behind it. So here, although we defined both period and also the shift indicators differently, it's still contributing to the same predicting power because it's representing this time series at the same definition or the same same fine resolution of time scope. Here, the resolution of time in the original data sheet, that's the leftmost 4 columns, it's on the day and shift level. So it has 5 days in a week and 5 shifts on the day. If we represent the day and also differentiate the shift, that's already the finest resolution we have on time. So defining the period using the number of days elapsed plus an indicator for the shift on the same day is the finest of time resolution we could go to. If we define the period using the number of shifts elapsed, it's not adding any additional information. It's still that each observation was differentiated or recognized by the period and the shift. It's not adding any further or finer resolution to the time horizon. That's why defining the period using days instead of shifts is not losing any information. That's why these two models, although they use different reference categories for shift, and they also use different ways to define period, it's not giving any different information. However, when interpreting the coefficient, this second way, period 2, does add some convenience. So when we go into period 2, we notice that it's possible to switch period without changing shift, or we could change shift without changing period. That makes the meaning of the coefficient more appealing. So, for example, now we could possibly move in terms of shift 2, holding period constant using exactly the first top row. So in the first top row, it's Monday, first 2 shifts, right? So between these two observations, we notice that the index of period are held constant. That's 0. That's because they are on the same day. And also shift 3 to shift 5 indicators were also all held constant because none of them were describing shift 3 through shift 4. Instead, shift 2 could actually switch between 0 and 1 without changing the value of the other predictors. So here, the specific way I define period 2 is somewhat more appealing than period 1 because of the convenience of interpreting the coefficient. So here, when we describe the shift 2 coefficient, I would say holding for the same day, shift 2 would have 18.1 fewer customers visiting the bank compared to shift 1. So notice that when doing the interpretation, we first hold every other predictor or every other independent variable constant. This constant could be any value as observed in the data sheet. So holding constant other variables when we describe a shift 2 coefficient means that we hold period so that it's on Monday in the first week, or it's on Tuesday on the first week, or it could be, the last day of week 2. Any of them would work. And also, we also hold shift 3 to 5 indicator to be constant. And in this case, this constant has necessarily 0 value because we could not possibly hold all of them at value 1, right? One shift cannot be at the same time shift 3, shift 4, and shift 5. So we could hold shift 3 to 5 at 0 because when we talk about the shift 2 coefficient. So was it clear how we could interpret a coefficient for time series models? All right, glad to hear that. It seems we successfully addressed part A while adding a few more pieces of knowledge regarding time series regression. Are you all good with part B and C? Any questions?
No,
All right.
I'm okay. I don't know if anyone else is.
Yeah, I'm okay too.
I do have a question, Jerry. It's T.
Okay.
Could we go back to question 1D?
Okay.
I think I'm not setting up my equation correctly, so I just wanted to ask, and I know we covered this, I think, in like homework 4, this last homework, but I just
Okay.
want to double check. So when setting up the equation, because we have a quadratic column, right? For when we're setting up the equation for the quadratic value, when we multiply it times the weeks, it should be squared, correct?
Yes.
Okay, I'm
Correct.
just double checking. I'm overthinking it.
Oh, okay. Yeah.
Okay,
This
thanks.
is exactly what this formula shows.
Perfect, thank you.
Yeah. In question 1, we have a week and the square of week. So this is week, this is square of week. So when we go to 16, square of 16 would become 265. 56, sorry. Yeah.
Okay, perfect. Thanks for validating me.
And in a different session, we also know one student asked if what seasonality means because they noticed that this shift was shift within one day. It's not a season. So so this might be that the jargon or the term seasonality is somewhat misleading. It does not necessarily indicate 4 seasons in a year. It could be anything periodical. It could be a day of week. It could be day of month. It could be also afternoon, morning or afternoon in a day. It could be peak hour versus non-peak hour in daily traffic. It could be also mean month in a year, or it could be quarter in a year. So don't confine the understanding of a seasonality or seasonal to be just 4 seasons in a year. Then it brings a question regarding how many different seasonality could be detected from our problem 2. We notice that we do have weekdays and we also have shift in a day. So possibly we could generate both seasonality. One seasonality comes from a shift within a day, and a second seasonality comes from day of week. So I built another two models in a similar way as what we did previously. It's just that here I also added day of week as additional variables. Because there are 5 business days in a week, that's why I used 4 different indicators, just as how we build shift indicators. Because there were 5 shifts, we used 4 dummy variables to represent this categorical variable with 5 levels, right? We do the same thing with day of week. So on the left, I used the shift 2 to 5 as a shift indicator, and Monday to Thursday as a day of week indicator plus period 1. To the right, the model used period 2. Notice that period 2 is number of the days elapsed, and period 1 number of the shifts elapsed. So we notice that they also exactly share the same R and R squared, because as we discussed earlier, the resolution of time in our original observation is just shift per day, so 5 observations per day. Either model has exactly the same resolution, so neither of the two has more or less information. That's why the predicting power is the same. However, because I defined period 2 to be different than period 1, the coefficient for different 2 is noticeably different. But we also notice that the other coefficients are almost the same. This is because period 2 represents 1 day difference, right? So when we describe a period 2 coefficient, we would say that holding everything else constant, but notice what everything else means here. So without changing the shift of the day, without changing the day of week, we compare 2 observations. How could this be possible? So let's go back to what the sequence shows. If we are now changing the shift and now changing the day of the week, but we want to change the period, it appears not possible or not that straightforward. If we move from, say, period 0 to period 1, we are necessarily changing the day of the week. So we could not possibly genuinely changing period 2 without changing these day of week indicators. So sometimes this happens, and it makes the model interpretation somewhat not so easy. So, but that's usually why we use holding everything else constant, moving 1 day ahead would observe 1 additional customer. But if we think deeper into what does holding everything else constant, sometimes it may not always give a clear interpretation. So pay attention to this part. However, it doesn't hurt in terms of prediction. When we do predicting, we are going to add a period with the day of week indicators and shift indicators, so we are not losing any information. And oh, right. I also recalled there was one additional practice question we did using this week's 2 problems. So let's also do this challenge here as our ending step for our review session. I would like you to think about this question regarding both problems. which of these models you have built so far do you think indicate causal relationship? Any tentative answers? Notice that I built 4 different models for problem 2, and I also have 2 different models for problem 1. Which of these do you think represents a causal relationship?
I think the one when you had period 1.
Oh, okay. Why is that?
I think because in period 1, you're having the days of the week and the shift. Well, I guess the days of the week aren't really being considered. Like, to me, the period and the days of the week are somehow like correlated. And in the model with period 1, you can't see that. But with period 2, you can. Because you have the 5 shifts being spread for each day.
Oh, okay. I'm not sure whether I captured the essence of your answer.
It's
But
probably wrong. It's okay. Go ahead, Jerry.
yeah.
I tried.
You're right that some of the variables are correlated, but this has nothing to do with whether a model shows causal relationship or not. And some other students previously reasoned that they believe, for example, in this case, they believe this second order polynomial model shows causal relationship, whereas the smoothing, exponential smoothing does not, because the yellow line fits better. And for the problem 2, they considered, I forgot how they reasoned. Okay, they considered all of them to be causal relationship, but however, the answer is none of these variables, none of these models we built so far show any causal relationship, because they are observational data. Notice that whether a model reveals causal relationship has nothing to do with the model itself. It's related to whether the data was drawn from an experimental design. In our both problems, shopping mall or bank visitor, they were just observed over time. There were no experiments done. We did not hold a control group, whereas do something else with experimental group. So we did not have any experimental design. That's what makes the data, the observations, to be observational, because they do not reflect an experimental design. That's why none of the models, whatever you build from the data, no matter how intricate or advanced your model could be, will not reveal any causal relationship at all, just because the data generating process, the way we acquired the data, was observational. Did you find that to be surprising or at least clear so far?
Yeah, I think it's a real-time application, whatever you are explaining, right? The way they derive data is based on what they want to read from the data. So if they have experiments set up, they already want to see if there is a, a correlation or a causation between the 2 variables. So the data will be set up in that fashion. But this is just recorded. This is actual data that's recorded. I mean, not randomly, but not keeping any of the conditions in mind.
Yeah, you're right on that. So notice that when you say actual data, when we do experiments, it's also
Yeah.
actual data.
Oh, yeah. Yeah.
So how the experiment was designed or how the data or surveys were implemented affect what type of relationship we could review. With this type of data at hand, showing how the number of visitors to a shopping mall and a bank varies over time, is simply observational. So it only reviews observational relationship, or usually we call that association or correlation, you could call it that way. Adding more variables or making the R squared larger won't change the essence of the relationship. If you observe, for example, one model shows a slightly lower R squared, whereas another one from the same data shows a higher, it doesn't make that the higher R squared model causal, whereas the lower R squared model not causal. So for example, if we compare these two models, without the day of week indicators, we notice that the R square is 0.89, right? Our adjusted R square 0.88. If we go to the one that with additional variables added, so nothing is removed, but more variables were added, it gives a relatively comparable R squared. Now it becomes not, instead of, well, 0.894, it's 0.897. It's minimally increased. However, you also notice that our adjusted R square is instead lowered. This is an indication for that the added variable Monday to Thursday are not contributing significantly to the predicting power of the model. So we could safely remove these variables without hurting the predicting power. So if you want to know more about what adjusted R square represents, feel free to go to my review session notes and make a search adjusted R squared. Yeah, so I provided a few notes and reading materials about what adjusted R square represents. It's compared to the simple R squared, it's penalizing too many variables added to the model. So it prefers a simpler, or what we usually call more parsimonious model. All right, that should sums up our week 5 discussion. I hope you enjoy a wonderful weekend.
Thank you, Jerry, for your time.
Thank you, Jerry. Have a good night.
Thank you.
Good night.
Bye.
Good night. Have a good weekend.
Bye.